precast, right? Basically attaching elements together. I talked about the emulation. I talked about the jointed concept. So today's subject is more focused on seismic, and I want to focus more on what advancement has taken place. And then I'll come back to the non-seismic and see how some of these systems could be utilized as well. So when you're looking at seismic design, you typically look at how the structures should be positioned for seismic load applications. So what you see here is a 6-story building. They have 5 bays in one direction and 3 bays in the other direction. So it's a rectangular building. So think of this as a precast structure. What you should be looking for is, so just like you do for cast in place, you will calculate the seismic requirements, which is basically equivalent of how much total load one should resist for that particular structure, or one should design for the building to resist. So, if you say you have, pick a number, say 1500 kilonewton, lateral force is something that you need to resist. Then for that 6-story structure, you could choose to resist that particular load through a frame structure or a wall structure. So in this particular building was designed by a professional designer in the seismic region. She designed this structure for a location in Los Angeles, and she chose to use moment frame, seismic moment frame, specifically a hybrid connection going in one direction, whereas so if you look at, I don't know if it shows up, but yeah, if you look at in this direction, so every frame here is a moment frame. So in this particular loading direction, these frames were supposed to take the load. So from a design perspective, I want you to realize that inertia gets generated primarily at the flow levels. So all of that load has to be transferred to this moment frame as well. So that's how you should think through. So in other words, the compatibility in terms of load transfer, so whatever the load gets generated on the floors have to be transferred to these gravity beams and down all the way to this frame. So the connections, I think we talked about it on and off again in terms of how important that is. Then your purpose should be to take that load and transfer that load to all the way to these frames. And they provide the resistance. So these floors can be attached directly to these frames, but this interior load has to be transferred to the outer frame as well. At least half of that comes here, half of that goes here. So once you make this seismic frame, so you only design this to be the seismic frame, and then rest of the frame, so you see it's a column, there may be beam running here. These are all what they call a gravity load processing frame. So the goal is to take the load, transfer to the seismic frame. But if this frame is moving, say, it's designed to move by say 150 millimeter, these columns have to go through same movement as well so that they don't collapse or they don't unseat beams. So some of the pictures I've shown you from Northridge earthquake in '94 is when they tried to do it, the unseating took place. Unseating took place, or 1 or 2 columns collapsed because they were not designed to take the load with the lateral movement, even though it's a free movement. And due to P delta force generated, they ended up collapsing. So the moment you collapse some of the columns, in one of the parking structure, if you recall, collapsed some portion of the flow system.
Good question. So can the entire load be resisted only mostly now here, in Hyderabad? They don't have a moment resting frame. they design mostly 90% of them to only the wall.
Yeah.
So in this case, probably you want to optimize the wall. So
Well, I think typically we wanted to promote both ideas and then let people decide how they want to do it. So I don't know if you know Susie Nakaki. She used to be with Engelkirk's office. And she's a big push. I mean, she kind of retired because of some health issues. She pushed big time in terms of precast, systems in seismic regions. She designed this structure. So she chose to show I would use a frame in one direction. And I think in some buildings they actually done that in terms of, because for her it's more important to promote both ideas, so that if somebody comes and say they want to have more openings, they prefer the frame, she has a solution, and vice versa. But I think if you give a choice, they probably will pick a wall. Like parking structures and things like that, wall is much easier to use, and they will use for the majority of the time. So
this SDCG category is a classification.
yes, yeah. So that's a seismic design category. That's what. So code has kind of changed. So, but the time she designed, that's what she.
something like our zone 4 as well.
Yeah. Now, so you calculate the total force, seismic force, and then half of that goes to this frame, half of this goes to this frame, and then you take this frame. So in terms of quantifying the moment demand, shear, everything is the same as what you do for cast in place. But when you design the connections, then you choose the jointed connection with hybrid concept, where you will have a post tensioning in the middle, and then rebar for energy dissipation. Now, in the transverse direction, if you like, she calculated the force. So let's assume that force was 1500 kilonewton in the transverse direction. And by the time she came up with the wall dimension, so you can see wall goes from this center line to that center line of the members. So the wall is going from here to here. She was able to provide, she only needed 3 walls, not 4 walls. And she didn't want to shorten the wall, so you could see she positioned 2 other walls on the outside of the elevator structure, and then she could pick this location, this location. There are 4 other walls, but she chose to put this one. So I just wanted you to know that they are not symmetry, but she wasn't concerned about adding another wall. Instead, to look at asymmetry, what would that create? But in this particular case, asymmetry also would put in some additional load in the frame, and they have the capacity to take. And so purposely she chose to maintain that asymmetric detailing, because all she wanted was the 3 walls. Under seismic conditions, obviously the earthquake load comes in a different direction than what we assume, right? So the asymmetricity will also come in, even if you design them to be symmetric. The load can exercise the building into a torsional modes and things like that. So it's not unusual to see. So don't force the structure to be symmetric and things like that, because that's not going to respond. But you need to pay attention to the fact that the asymmetry will come in, and then that you have to deal with it. So once you decide that, then you take the frame and do the moment resisting frame. So the hybrid frame, this particular structure, as well as the wall with energy dissipation, both are now accepted into the American Concrete Institute building code. They call it special wall system and special moment frame. They don't prescribe, but they refer to what they call, it used to be an ITG, now it belongs to a committee, the particular document. So they say you're allowed to use it, and you have to follow these documents. So that's one thing that if you're going to start the process, I don't know if the Concrete Institute allows this, they will create a document on its own. So you look at what people have done, they look at what test needs to be done, maybe you do some test here, and then you develop a guidance, and then they don't integrate that yet, but they say this particular system is allowed as long as you follow this document that you guys can kind of maintain, right? So you develop and then you maintain. Because as research, more and more research comes up, you want to decide any fine tuning. So once you put into the code, it's, I don't know, system here, it's harder to make changes there because then I had to go through different committees. But it's reference to a committee that's more responsible for precast. They can fine tune. One point you feel good and then you can, incorporate it. But I don't believe that up until now, these documents have been separated from the actual standards, but they reference these one in the main 318 refer to these documents. Now that 319 came in, this has not been incorporated yet. I could see this is going into the 319 document down the road.
So here also we have a say. The committees come up with the design guidelines, not really code per se.
Yeah.
Quickly, that's much more quicker.
Yeah, they start as a guidance, but if you have a specialized group or specialized industry, they could influence in terms of the importance of that document, and so they can acknowledge it in the design, design code. So I assume like for legal binding, you need to have some official guidance in terms of what's you're allowed to use and what you're not allowed to use. So guidance are kind of, so when you only put it as a guidance, you're not required to follow by law, right? So if you use the guidance and if something happens to the structure, then you have to defend as to why you use the guidance. If it's by the law, then you say you follow the structure. Then it's about did you apply the provisions, satisfactorily? That's what would be the question. So what I want to do for most of this morning is now isolate one of the walls, and then we're going to detail it in two different fashions. One is with a controlled rocking concept, right? We will have unbonded post-tensioning. That's what we have been promoting. So if you want to emulate, you're not expecting high seismic, you basically design it and put couplers and you have the wall, right? I've already given you a paper on emulation concept that you can follow. Do you have guidance here for the emulation concept or something equivalent? Okay. Some work has been done in New Zealand after the Christchurch earthquake because of the failure. So if you're developing something, you should look at those stuff that came out. One of my former students is the one did some of the work. He's a faculty at University of Auckland. Maybe I should invite him to come to that structures congress and talk about it next year. So that's something to pay attention. And then length, even in teammates, I saw the length of their the duct they place in the base of the wall is pretty long. So they will kind of keep most of it, undamaged. And then forcing interface, and so the forcing interface, I think we've seen pictures of things like that. The shear sliding has become more and more of an issue at the interface, which we saw that in the New Zealand event as well. So it's good to bring those things into the design practice as well.
So see, I think it's the only with the wall, the major, as you said, architects, they don't like to have the walls
Outside.
So as the structure becomes more and more asymmetric, then you need to rely on these moment resting frames.
Yeah.
You cannot really get away from them.
So, precasters, if you give a choice, they prefer the wall, right? Because it's easy for them to deal with it. Moment frames, the connections, number of connection increases, then they have to deal. So like in this case, 3 walls, all 3 identical. They are cantilever type wall. Construction is easy. Post-tensioning is easy. Energy dissipation, you can manipulate those things. Hybrid frames, you got a lot of moment column. You got, I think how many ways you have. So you got, 1, 2, 3, 4, 5, 6, and in 6 times on both sides, you're looking at 12 connections, and then you have 6 stories. So they add up in terms of the, and then control, maintaining quality control. Every connection has to be done properly. So it's If you give them a choice, they prefer the wall. And they tend to move the walls in like what you see here. So it's a simple structure. That's what she did. She moved the walls inside so that it's not an issue. So you could do walls in both directions, interior, if that's a possibility. The precast has not been taken to building core walls as such. I mean, that's one area I think it's worth pursuing, and because of limited application, I'm not really all excited about moving that direction, like a U-shaped or T-shaped walls. How do you establish a connection? So if it's a rectangular pieces, how would you establish connections, the energy dissipation? That area has not been looked at. So typically if you're putting walls, they are individual rectangular walls is what precasters tend to do. So you have given, so this is in a high seismic region. So let's focus on the walls. We chose to put in, or at least the designer selected 3 walls. And if you calculate as per the current design code, what happens is the amount of damping that requires, which I think is 18%, means that you have to add some damping to the system, right? Because if you just have only the wall, that won't have this 18% that they're looking for. So as you can see here in this particular case, it was designed to be as a pre-vec system, as I said, so it's a wall with in columns. And then these elements are the energy dissipation. I think you saw that last time as O connectors, same here. In terms of the dimension of each of them, whether you distribute evenly, or in some cases you don't want to distribute evenly because you don't have space here. So for example, you can terminate the N column here and keep the energy dissipation only here, but not necessarily at the top. So all of these are possibilities that you have to analyze and figure out how you want to place them. But in this particular case, it's shown as a kind of a evenly distributed connector elements. So these walls, the dimension that you see, as well as the amount of post-tensioning, which I will show you more in terms of the details, are sufficient to resist the loads that were calculated for this particular seismic region. The energy dissipation, as I said, the goal for introducing these O connectors is that you could, so in this case we have 4 in each floor level, so that's 24 units. You could increase the thickness of the O connector. You could change the dimensions, or you could just have only 2 of these. As long as you prevent them from buckling in the outer plane direction, they will provide resistance or energy dissipation. Plus, it will provide some additional resistance as well. So if you're doing connections, you must focus on making sure that these connections are easier to install, it's cheap, it doesn't add more costly or more expensive quality control issues. You know, people throw a lot of things, ECC and this and that, but you send the detail to somebody up in the field, they probably don't know what ECC is. And I don't know, I've seen it, people tend to put more unnecessary things that increases the cost, and then they say it's become too expensive. So keeping it simple is important, and that's one of the things that we also emphasize to make sure that the cost will not be excessive here. Okay, so we talked about the 18% magic number. That number was given by a committee. They came to a consensus and said that should be acceptable. They were reluctant to go lower, and they didn't enforce us to maintain like 20% or 25%. And we were able to fight back saying that, hey, we have done tests to show lower damping should be adequate. So what I wanted to do is, I wanted to just look at a series of tests to see how well these numbers translate. Now, we could put 0% damping, right? Just get rid of all of the connectors, then you will have 0% damping. So if I put 0% damping, where do you think the damping is going to come from? So when I say I put 0% damping, I get rid of the connectors. I'm not supplementing any damping. Will the wall has any damping? So if you push on a structure, or if you bounce a ball, does it bounce all the time? The energy gets dissipated, right? So if you take a concrete wall and rock it, it will come to a zero displacement after several seconds. So each of the structure has inherent damping. Some are at the molecular level, some are opening of cracks and closing, some have bolted connection, the friction induced, the thermal energy dissipation take place. A lot of things happen. We typically assume that number to be in the 3 to 5%, we say, right? So the damping is an important piece. Make sure you understand that any structure will have 3 or 5% damping, right? What we are providing is what's known as a static hysteresis. We throw in supplemental damping. It's a deformation-dependent damping. The other one we talked about, what is inherent is we approximate it as a velocity-dependent damping. So they have different damping, different mechanisms. So one is a velocity-dependent. This is a displacement-dependent. So the more displacement the wall goes through, the more damping you're going to get because more plastification is going to take place. What other damping you can think of in the system? So we talked about rocking, right? So I touched on this last week. When a structure rock, it bounces on the foundation and bounces back again. So it goes to the foundation with a certain velocity. It goes through a certain angular velocity and bounce back with a slower angular velocity. So every time it hits on something, it loses energy. So the impact damping will also be there. The question is, can all three damping be counted as an additive to figure out what the total damping is? Because remember, one is a velocity dependent. The impact is also velocity dependent. This is a displacement dependent. So we didn't believe that this damping, all will exist at the same time. So I'll give you an example. If you put in a hysteretic damping, like through this energy dissipating element, this actually alters the velocity. So if you alter the velocity dependent damping now is going to be different. So there's interaction takes place between damping also. One will affect the other one. So you cannot calculate everything separately and then sum the three to say, okay, this is my total damping. It doesn't work that way. So it's important that you understand where the damping is coming from. So when you do testing in a quasi-static manner, like I've shown you, right? We test push and pull slowly. That basically doesn't induce any velocity-dependent behavior. So you don't get any velocity-dependent damping. So in that exercise, what we try to do is we quantify the amount of static hysteresis in the system, right? If it's a column, you're pushing and pulling, plastifying, it tells you what the static hysteresis is. In the test that we conducted under quasi-static, what we mostly got was the equivalent damping coming from, so that alone is an 18% is what the committee was asking. The question was...
Predominantly the material damping which are displacement.
Which one?
You said the hysteretic damping is predominantly the...
It's a displacement base, right? So they have to be displaced to plastify, whether it could be reinforcement, it could be this connector. So all of those things are displacement dependent. So when you do a quasi-static, like I will be doing some testing in the lab, I will say earthquake testing. People walk in and say, you said earthquake, nothing is shaking. Because I was quantifying, okay, how much static hysteresis damping I'm getting. It doesn't matter. So in fact, if you do under actual velocity, then you get both damping comes in. So you need to then separate which one is which. So the quasi-static test itself has some value in terms of giving you how much damping it has. But what we need to be careful is that it actually alters the other damping as well, potentially can alter it because it alters the velocity.
If I really want, if this, I remember you were telling, typically we target for 30 to 35%, right? So if I want more, then I can actually bring in some dual mass dampers and all that.
Yeah, I mean, but these things you can add more connectors, you get more damping, right? But again, the 30% damping is not a requirement, right? No. So what happened was, it was back calculated value. So back calculated based on tests people have done. So let's say you are building a column for a bridge. The seismicity requires certain moment resistance. So you put in, like I don't know what the bar size is, say 22 millimeter bars, dozen of them you put it. That was controlled by the moment demand. Now, the energy dissipation associated with that comes with it because you already decided. You decided the moment resistant, the plastification of, if you have 20 bars, they are providing. I'm not controlling the damping. But since these structures are performing well, back in the days, they calculated the equivalent viscous and said, okay, you should have 30%, then everything is going to be fine. But now we are separating the damping. We don't have to follow that was the one fight we had to start with. Let us decide how much damping is needed. Don't tell us 30% because you back calculated 30%. So that was a misconception. I think people shouldn't have started with that. Like if it's a cast in place, it's the damping, the stiffness, everything is determined by the time you determine the amount of bars that you need in the base of the column, for example. So that was the misconception because everybody initially, even if it's a tuned mass damper or base isolation, they all said, okay, we need to come up with a 20% damping, 25% damping, because that's what the cast in place are doing. But that's not a good reference to start with, is what I'm saying. So what we wanted to study was, we wanted to study series of walls. One set was just like what you're shown. So what our designer designed in terms of pre-vec, she specified 18% because that's the code asked. We told her to do what she will do based on the code. So she did some numbers, came up with the pre-vec system with certain number of connectors, and then said this should be satisfying the design requirement. The second set of walls, what we wanted to do was eliminate all of the connectors in the structure and say, okay, we provide zero damping through hysteretic action. You just rely primarily on the inherent viscous damping and the impact damping. If you do that, will the wall survive? I mean, that's a good question to ask, because if they survive, they are going through less damping. So the things that you should expect is, maybe it's going to displace more. If it's going to displace more, by how much? Maybe it's going to go through more number of cycles than this one, because this one has more damping. So if that's the case, how many more cycles? Is that going to cause low cycle fatigue issues to the structure? But those are genuine questions to ask. The reason I want to compare and contrast the two systems here is that if you can rely on the other system, you can actually use that for non-seismic applications, right? Non-seismic application, 5-8% damping is more than enough. That's what we don't calculate, we don't design, so there's no reason to do it. So we wanted to influence. So if you have if you have more walls in this structure, so for some reason they had a gravity-bearing walls, they could be just designed to be post-tension, unbounded, just let it go for the ride. Don't do anything, because it's cheaper to do it that way. Now, you don't want to throw those walls and put a couplers and make them rigid, because then they will be restraining the movement and they will start dissipating, or they will start to resist lateral load. That's not what you want to do. So it's easy to create a pin system for a wall structure. If you run unbonded post tensioning and let it rock, it's almost, depending on the location of the pin, you could, location of the post tensioning, you can make it as a pin type connections. So make sense? Yes? Okay, I don't want them to lose. Okay, so I want to look at some of these tests. This was a series of work done by another student of mine.
So what kind of things that we need to ensure? The gravity system also rides along with this, as you said.
So there had to be displacement, so one, you have to make sure that they are displacement compatible, right? So they have to go through the motion without resisting loads. I mean, you get small percentage of load, you can calculate and see how much it is. So that's one thing. The other is a shear, if it's a pin, if there's no load is going through, then the shear will not be an issue. So there's not much to be done. It's a deformation compatibility is what you want to look at. From, like, these walls are going to be transferring loads, gravity load from the flow system, for example. So there needs to be a connection. The connection has to be able to accommodate that deformation. So as the wall rock, beams are going to be deforming. Can they go through motions according, things like that has to be paid attention. Okay, so let me just go back to what we were discussing previously. Let's see. Okay, so this is the type of structures that we are trying to match. Cast in place, wall. So the 3 walls I talked about. Now I have, the 4 choices I discussed Friday, right? One is a cast in place, that's this version. The other one is an emulative. We talked about emulation, how you would be doing, that's a possible path. The third one was a free rocking. Free rocking is not a possibility because it can become unstable. The last one is a controlled rocking. So I'm basically going into the controlled rocking phase and want to compare what I was able to achieve here with the controlled rocking. So that's what we are looking at. With the controlled rocking, the question is how much post tensioning you want to put in, and then how much energy dissipation you want to put in. Those questions remain to be answered in terms of, so amount of post tensioning is typically done fairly easily because the moment resistance will dictate the amount of post tensioning. The amount of post tensioning steel depends on what initial stress you want to maintain, and we will talk about it a little bit more later. So we did 2 sets of tests. This is what we call a single rocking wall. So if it's a single rocking wall, all you have is a post tensioning in the middle. The moment resistance comes from, tension here and compression there. That couple provide the resistance, right? If you want to keep this wall as a gravity load bearing wall, no lateral load resistance, you could reduce the amount of post tensioning, and then you could also, doesn't have to be rocked this way, you can cut down the interface. I mean, that's something that's typically used in the US, mostly in the bridge folks do that quite a bit. So, if you want to have a column, and this is a foundation, if you want to, same applies to the wall. So if you want to cut down the amount of moment resistance but act as a pin, you could leave a gap here. So typically they will put in some deformable foam, and then they'll run the cable, they run the reinforcement in the middle, so the lever arm is now reduced. And so it's going to be act as so you could cut down the resistance by 90% or so roughly by adjusting your contact area. So you could do something like that.
But then for the same, you said for energy, we study tapping, this fellow will go for a lot.
No, yeah, well, that's what we want to investigate, right? To see how bad it gets, right? So now what I'm saying is if this is going to be a gravity column in the precast structure system, wall is providing resistance, columns have to go for the right. So they don't have to provide energy dissipation. They have to be deformation compatible.
This is your column.
Yeah, well, column, we can do it for the wall also, but not as a seismic resistant gravity system, exactly. So these are the features now we are pushing for, right? So this is very different from cast in place. So again, we are tackling precast as a precast element. We are not comparing and contrasting it. This is what cast in place does, so I want to make it emulate what cast in place does. No, we are not doing it. We are just taking it as what can this wall do now, because we got this concept, the control rocking concept. We know that we can provide adequate force resistance. We can provide recentering capability. I've touched on it. If you're not clear, let me know. I'll go into that with more detail. And then we know that I haven't put any energy dissipation element, and the inherent damping in the system will be less. In the past, people ignore the impact damping because impact damping was difficult to quantify, and most of the tests were done in a quasi-static manner, so the impact wasn't in the picture that it's a possibility, right? So the alternative is, you see in these pictures, we do a jointed wall like this, or you use a hybrid at the base. Instead, we introduce the pre-vex system. So our goal was to look at, so this is better than this because this is jointed. It may reduce the amount of force resistance. Single wall is better, but then we need to have replaceable energy connectors, so we ended up with a pre-vex. So the goal is to see these are designed to match moment resistance of cast-in-place wall, but how will they perform under earthquake load? That's what we were interested in.
So what are these hybrid walls?
So they call it hybrid walls because they have unwanted post-tensioning and then rebar. So in the hybrid movement frame, this concept was introduced. So they took that here and call it a hybrid wall. There's nothing magic about it. But we argued that that concept was, could provide, but you cannot replace. You cannot. So these are supposed to be what we call a more resilient system, provide functional solutions. So after the earthquakes, you can use them. But if you had to replace rebars, and there's no way it's going to be cheap or possible to do. Whereas this structure was designed, so just so understand, this structure was designed with sufficient amount of damping. You designed the amount of post-tensioning, so there's a portion is going to be taken by this, a portion is going to be taken by the connector in terms of forces. The combination of the two will be designed to resist the seismic load from a large event, whatever the large event that for your region is. Magnitude-wise, or what the code specify as design level earthquake or maximum considered earthquake, you deploy both of them. But then the lower level seismicity, we make sure that only this is needed, this is not needed. The idea is that after the earthquake, we can replace them, and if there's any aftershock, this alone should be able to sustain the resistance. So you don't need to panic or building is not going to come down. That was the whole concept. Make sense?
Hybrid wall exactly cast in place plus the system.
No, it is a precast, but this detail matches what was promoted in the hybrid connections. So they call it hybrid. Yeah, because the original idea was combining the two, the unbonded post-tensioning and cast in place. That's what the word hybrid came about.
Oh, okay.
But then the people modify and still call it a hybrid, right? Okay, so you will see these terminology SRW, which means single rocking board. There's nothing in it. Each is a single individual rocking board. This is preveg, which is this. So everything else in between we eliminated is because they're not something that we are focusing on. Our goal is to say, if I investigate this wall and this wall independently, both are designed to be compatible with or comparable with the cast in place, I will know what damping to put in, how much we need to rely on. Okay, I want you to just understand this a little bit so that you understand the evaluation better. So, this concept was developed 10, 15 years ago and then got modified and then now got into the design course quite a bit in terms of, so think of this as 4 different, so at any given region, they were initially proposing 4 different design spectra, if you like. The third one, which is called EQ3, I believe. What is it called? Yeah, EQ3. That is what we typically design for. It's known as the design level earthquake. And then the EQ4 is equivalent of maximum considered earthquake. So if you're doing a performance-based seismic design, you'll be designing it for both cases, one for the design level and one for the maximum considered. So design level mean it represents an earthquake every 500 years, let's say, whereas the EQ4 is, at least in the US, is once every 2,500 year event. Is that the same here, or you only design?
Simply say 2005, 2007.
Okay. Yeah, somewhere in that number, right? So since we are testing it, we wanted to make sure that it can not only, so we design it for this, but we wanted to make sure it also can survive that particular maximum considered. At least we wanted to know, can it survive a maximum considered event? You also see EQ1 and EQ2, those are more service level type of earthquake. So if you have service at the service level, like a frequent event that is a concern, you should be looking at EQ2 and making sure. So for example, you could choose not to have the connectors activated if it's an EQ2 level motion. So you can design the connectors to be with enough flexibility so that they remain elastic. So connectors don't go into any deformation if it's a 4.5. And if you go to Alaska, 4.5 is like every other day they get a 4.5. So you don't want those connectors to get exercised. So that's the whole purpose there. The other interest here is that not only we wanted to look at the seismic different intensity of earthquake as to how well the walls perform, but we also wanted to look at the energy dissipation aspect of it. How much is energy dissipating? Can we compare and contrast with the different system in terms of their performance? So in terms of design, so this was the original document, but they call an ITG 5.2, which is the ACI. So the ITG 5.2 is the document for the wall system. 5.1 tells you to do evaluation to make sure your system is equivalent to what is in the ITG. And then the 5.2 cannot give you the design method. It has some design assumptions that need to be improved, so we are working on that right now in terms of improving it. Yeah, I wouldn't go disturb that. So the other thing that we wanted to make sure is that we would eliminate any damage happening to the structure as we go through the seismic motion. Okay, so in order for us to do the test and evaluate the performance, there was a concern came about in terms of, so we are basically looking at three different type of structure. One is a cast in place, there's a single rocking bolt and the Prevex system. By just comparing like a damage pattern or extent of damage, it's hard to tell one is performing better than the other because we are plastifying different region, we are changing energy dissipation, so we had to come up with a different plan in terms of how we would evaluate the performance. So the steps that we have taken is design the prototype, so that's what our designer did. So she's a professional designer, so she designed them. She came up with the dimension for the test wall at the full scale. We created what would be the equivalent, because we did do a reduced size in terms of the actual test. Then we come up with a loading protocol so that we are not treating one wall different from the other. So for example, these walls won't have the same period. So if I pick a set of motion to bias towards one set of walls, maybe they will not perform well, but other set of walls would perform better because they didn't have energy, seismic energy in those frequency range. So we had to be, we had to think about a different different ways to evaluate it. So we spent some time coming up with a loading protocol, and then we have to come up with a shake table test setup, and every wall was tested initially on a shake table as well. So you've seen that, but the prototype was designed, so there are 3 walls. So on the table, what we decided to do is just put one of these walls. So total resistance, you know what each wall was designed for, and then we would design the wall. So if you have a Prevex system, the connectors provide additional resistance. So we will design that accordingly, reduce the post-tensioning if it's a single rocking bolt. So each was designed independently without looking at the other system, because that's how the designer will go through. So the other thing we needed to address was shake table test. You're basically shaking from the bottom, you can't build the floors, the table has limitations. So we took the 6-story wall, and from there we came up with what would be an equivalent single degree of freedom system would be, so that we can, so this is a concept that people use in the displacement-based design. You can take a multi-story system and come up with an equivalent system, and then that gives you an equivalent seismic mass, because that's what's going to generate this inertia into the structure. So you go through and figure out, this information has been published, and if you're interested, I think I may have included 1 or 2 papers with that too.
I think that paper will, speed up work when you...
Yeah. So there are some papers. So if you're going to do, I think like the single rocking wall, for example, you could use it for non-seismic quite comfortably instead of forcing these, but the anchorage issue is one we need to do. So if you're going to do any test, first test I would recommend, get some strands and wedges and do evaluation on that. How can they survive? You can do a fatigue evaluation, you can do those things.
What do MDO and SDO stand?
So the MDO is a multi-degree of freedom system, which is actual building. And then we created a single degree of freedom system. And then the scale worked out to be 1 to 3.6. This is dictated by the payload capacity, how we can manipulate the seismic motion, because if it's a scale testing, the hydraulic system had to be cope with the modifications that we do provide for the actual structure. So these are, basically everything is done independently, but in the same manner. So each one is tested with the appropriate set of parameters. So the point I want to emphasize is that I cannot calculate one set of parameters and go and test another wall with the same parameters, because they're not the same. So we have to calculate. So we have to look at it. How do we evaluate? How do we justify their performance? So what you see here on the right side is the single rocking wall dimensions. So the wall panel length is about 2 meters, or was that 236? Yeah. Length is about 75 inches, so it's just over 2 meters. And the height is, so when I say height, that's where the seismic mass was applied. Inertia was created, that's based on the height calculated here. So that was 14 feet, so it's like roughly 4.2, 4.3 meters. So this is how we did the test on these things, and we performed tests on 4 different walls. So you could see all of them are same dimension. We modify the initial pre-stressing by using 4 12 millimeter strand to, so 0.6 is so 0.6 inches is going to be 14 millimeter strand. Is that the
12.7, half inch will be 12.7.
Yeah, what is the other side?
The other one will be 15.
15, yeah. So we because the anchorage concern was brought up in terms of, if it's a 12 millimeter or 12.4 works well, can it do better, or can it survive some larger strands, the anchorage? So, and then there are a few other parameters we wanted to study. So we did look at those things. Because of the rocking nature, to prevent any damage at the base, in the past people tend to put in steel channels here, so that basically the channel is the one, causes the impact, rather than concrete to concrete. There was concern that if it's concrete to concrete, some damage will take place. So we had an official designer who is a practicing designer. Then we have 2 or 3 precasters who work with us. So they also dictated in terms of erection, prefabrication details, performed the actual prefabrication. They also looked at the detail and made comments. One of the things they said was, we don't like the angle at the bottom. Their concern was 2. One is anytime you add something, it increases cost for us, so eliminate it. That's one thing. The second thing, which should be a concern for you also, corrosion. If the wall is on the exterior of the structure, the corrosion becomes a nightmare, and then you have to deal with that corrosion problem. So we did initially start the details with so when you say 12 inch at both corners, that was the length of the channel that put in, so it's about 1/3 of a meter. And in one case, we put in, I think it was a requirement came from one of the precasters to use I think it was argued that putting a channel for the entire length is a better option. So, and then by the time we understood what was going on, then we eliminated the channel completely because the precasters asked this. So here's a casting of the single rocking wall. What I want you to focus here is that if you are casting the single rocking wall, they're going to rock. The resistance comes from at the base, basically, post-tensioning and compression. And the amount of reinforcement you need, so that applies in every section, you really don't need much reinforcement in the structure. So the only steel that you see here is a shrinkage control reinforcement. So cast in place structure will look very different, very congested amount of reinforcement. So now we're taking a precast, you're going to rely on jointed concept, we are going to allow it to rock, and look at how much labor one can reduce by getting rid of a lot of the reinforcement. There's no reason that we believe we need to have more reinforcement. We did put some confinement reinforcement in the corners, so that's the only additional steel was put in. You could see, because that's a region basically get impacted during the rocking. So we can calculate what the contact as it reaches a certain displacement, and that region was designed with confinement because when you rock, obviously you're going to get pretty high forces into that rocking toe, and I wanted to make sure that we provide adequate reinforcement. But I think if you have done some seismic design, this is nothing compared to what a cast in place confinement details will look like according to the design codes. It's much more significant. So if I look at the cost of this wall, is much cheaper than a cast in place wall also. These walls initially was put in a pocket, so foundation will have a pocket and the wall get dropped in. So in the US, unlike here, you will have a precaster, you have a structural designer, and then whoever erect the building could be a third company. I think here it seems that everything is done by one company. So the erector also will come and look at the plans and make some suggestion, hey, this is what I'm going to erect it, this is what I want to look at it. So they prefer this pocket so that the wall can be put in place. They can shim it on all four sides to keep the wall straight. So they like the idea. Structural designer prefer it because the shear, the sliding could be eliminated by doing this. There's no way the wall is going to walk away. Precasters wasn't that crazy. Precasters said, anytime you create a pocket like that, it costs us money. I mean, in the US, its cost drives everything. So they said, we can do it, but eliminate it if you can. So we did eventually eliminate it to show if you want to eliminate it, you can do it that way as well.
This wall was made as a single piece. Why
Single.
not to provide the horizontal joint in the middle?
Because that has been studied already. So when they connect pieces like this, in fact, the designer actually detailed it as, I can't remember, it was 2 or 3 volt. So what they do is they do exactly the splice detail what we have seen here. They will bring the rebar sticking out, and then they will put a grout pad, drop the next wall, and then they grout it. Because they don't open, they don't crack, it doesn't cause any issue. So that's pretty commonly used. The problem is if you're starting to open, if you're critical moment region, that's where like the plastic hinge region has become a challenge once you modify it. So I want you to understand and appreciate that we just walked away from the emulation concept. The wall looks simpler, the details are simpler. We can evaluate and make a decision as to how far and where one can use these systems. So if it's a Prevex system, we did the exact same thing, except that it was designed with the end columns. The end columns can be concrete columns, steel columns. It could be full height, it could be partial height. One of the huge benefit of having these columns is that you could also just transfer gravity load only through the columns and let wall to provide the lateral resistance. That's also a huge advantage the designer took advantage. Okay, so I talked quite a bit about the O connector. The few things that I want you to know about the O connector is that O connectors, so think of this as when the wall goes from left to right, this gap opens up quite a bit. This doesn't close, it compresses, but the compression is going to be much smaller. It's nothing like what you see here. So what you see here is an evaluation of the O connector for the expected deformation. On the tension side, it's going to go like this. On the compression side, which is this side, it's going to be compressing only a small amount. So it's a big difference. So they go through like a asymmetric motion. But you can see the hysteresis loop because the steel plate, they are pretty stable large loop. So this loop, for a given displacement or drift, you can figure out how much energy dissipation one O connector would give you. And then you can decide how many O connectors to put in. You can fine tune the design. The only concern with the O connector is that you want this to be performing in the in-plane direction. You don't want it to be moving in the outer plane. You have pretty slim plates, so they have a tendency to buckle outwards. Once they buckle outwards, it's hard to control the behavior. So we typically would provide restraint like what you see here. So it could be a steel plate welded on one side. It's like cantilever piece welded. So in this case, we use steel columns. So it's welded to the steel column. So it will prevent the plate from buckling outward. And they will deform in the in-plane. I mean, they're not significant forces in each one of them. And the outer plane force is also small. So restraining them is not that difficult. And so in this case, remember that we said the length of the wall is 75 inches or just over 2 meters or 2.5, maybe 2.2 meters. So we maintain that length. So from here to here is still the same. Single wall from here to here, because that's what I would have done the design in each case. So I don't want to increase the wall dimension because I'm putting an end column. So end columns is contained within the full dimension. So that cut down the wall by, you could say, is drop it by 15 inches. So, 7 centimeter or whatnot. That reduces the moment, the lever arm, so that will reduce your moment resistance, but you get additional moment coming in because of the forces generated along, due to the connectors. So that's how we provide the resistance. So the out-to-out dimension in both cases were the same. I think we talked about the outer plane direction. So in this particular case, it's the same thing. This is out-to-out dimension, O connectors. So you can see how the connection is established. It's pretty simple. It's a stainless steel it's a regular steel to grade 50 steel. So 50 is about 350 megapascal. You could see the connection is done only with the weld over a short distance. So if you look at, I don't quite see it here. So here's an O connector, and that's the only weld. So there's a weld here, there's weld here, and then same thing on the other side. In this case, they decided to use, so it provides some flexibility. So we added another column to provide the restraining, just to show that you don't have to rely on the wall if you don't want to. So there are different ways you can cause this constraint into the system. Let's see so this is another Prevex system. So in this particular case, we did another variation where we actually didn't, so you could see it's a different, so we were looking to see how many variations we can bring in. So in this case, the wall is actually 75 inches or 2.2 meters, but we put this column, you can see it's a pin-ended column, connectors were attached to it, so that way we maximize the lever arm of the wall. So if your space if you have space to incorporate details like that, you can do that, okay? So I'm going to stop here and then come back and give you a tea break so that you can wake up more, and then we'll come back and continue. Good?
What are those red buttons?
Oh, that's just the rebars for sticking out for cap, just to protect people from, getting hurt.
I'm not saying the caps, I'm saying on the wall.
These ones?
Yes.
These are LED sensors we use. Yeah, so these are, so each one is an LED, so it's a small disc. what they do is they can actually, it's a pretty good system. They can, they use like a 3-camera system, and they will monitor each of the LED where it's moving in the 3-dimensional space. Then you can create like a MATLAB code and figure out, strains or rotation or whatever. So I think the orange thing is a protection cap for this LED. We remove that right before the test. I use that a lot now, actually. Even for curvature measurements, you don't need LVDT. You can throw this one.
No, we try to use the 3D DIC. It's the same thing.
Yeah, it is. Yeah.
Simpler version of
This is that you don't have to spray anything.
Yeah. And plus, it does it in the 3-dimensional space, and it calculates based on the original. Once you have a crew kind of get used to it, I just have students train the other students and keep it going.
We can break now. Yes.
All right. So what we want to just continue the discussion a little further. So I just want you to see the different concept that we are exercising, the flexibility that these systems can bring in. So I want to talk about, so this is basically the detail we use to move the tube inside. Again, it's not possible in every structure, but this tube doesn't have to go all the way to the top. You can terminate it even within a floor, put larger connectors. There are a lot of ways you can play with these things. So for testing purposes, this is what we did. We actually did terminate, in this case, the connectors to the base level, so about half the wall for pre-bake system. This also set inside the pocket. There is a grout pad put in place, so you typically bring the wall, put steel shims in here, make sure the wall is leveled, and then you pour grout, and then it goes underneath it, and then establish a full contact. You could see this unbonded post tensioning is attached here, as well as attached at the top. So if you lose the strand, basically the wall will come loose, right? So that's why I think I've been emphasizing the post tensioning anchorage is important. So 2 things we have to do. We need to do, this is unbonded so that it can survive multiple loads. So you don't want them to go inelastic significantly. So these post tensioning steel are designed such a way, so I showed you like a EQ1, EQ2, EQ3, EQ4, 4 different seismicity. Under EQ3, we designed them to remain elastic. If you go beyond, you may allow some inelasticity to come in. And sometimes they will experience that. We also studied to show that if you lose the amount of post tensioning by 10%, 15%, it's okay. The structure will survive still. Here's the other detail. So the reason we partially terminated to show that you can actually keep all of the connectors within the first floor or 2 if you wanted to. Doesn't have to be extended all the way. When you put the beams or the end columns here, the advantage is that end columns could be then connected to the perimeter frame in terms of transferring load. The gravity load can go through here without interfering with the structure. So here is the 4 different walls that we tested in pre-vec. So again, the seismic height is the same. We did alter the seismic height to see if you bring in some change to the dynamic behavior, how well the performance takes place. We did play with the connector size. The connectors are the same size, but the number of connectors was changed to see if I change the amount of damping, will one wall performs better than the other wall, if you like. This wall also tested with the 1 to 3.6 scale range. Okay, so I want to spend a little bit of time in terms of the loading protocol. It's something that is important that you understand if you are a student, grad students doing graduate work, trying to understand. So when you design these structures, you want to you want to go through an evaluation in a dynamic manner. The question is, do you use recorded earthquakes? Do you use spectrum compatible earthquakes? Do you use simulated earthquakes, simulated loads out there in terms of, in some, like I assume in India, for example, especially if you come to South, you probably don't have significant recorded large earthquakes, so which one to use? Both have significance, right? Recorded earthquakes have significance because it has its own characteristic. Simulated earthquake has significance because you can match the simulated earthquake to match the target spectrum, so you're not exercising unnecessarily or putting too much energy into it. What we ended up doing is actually a bit of both, because we argued that these walls are designed for damage-free or survive without going through large significant damage. So therefore our argument is that it shouldn't matter how many earthquakes we run through. The only thing is that the test lab complains if we just keep testing it. So that's something that we wanted to focus on. So we came up with the 4 sets of earthquakes. So we had four sets of earthquake matching the EQ1, EQ2, EQ3, EQ4. Those 4 sets were basically actual earthquake, but its frequency content was modified to match the target spectrum. So that the advantage there is that it tells us how will it perform if you match the demand that you're looking for. Actual earthquake, but modify the target spectrum. Then we took some actual earthquakes. Instead of, we didn't modify any frequency content, what we did was we modified the peak around acceleration within some certain parameters. I'll explain that a little bit. So these are the 2 suite of earthquakes. The first suite is a spectrum compatible motion. So spectrum compatible means the EQ1, EQ2, EQ3. This tells you what the original motion was. We modified it to match this. So if you calculate the spectrum of the modified earthquakes, that's how so it matches pretty good. It's important to make sure when you match, how will it perform. So if you're doing analysis in a computer model, you should go through these motions, 2 sets of motions. We have published an article saying why this is important, what are the benefits, so that way you're exercising both sides to make sure these structures can survive. In a lifetime, not a single structure is going to go through all of these motions, but these are damaged, they are not supposed to experience significant damage, so we felt comfortable running as many earthquakes as possible. And then, in addition to that, we have recorded motions, and the recorded motions were done based on some of the recent events as well. So let me give you an idea about how the recorded motions were modified. So evaluated what the dominant period of the structure is. So that's the dominant period of the structure for a given wall. So the dominant period is determined by a secant stiffness. So from that stiffness to that stiffness, so that's defined. Within that stiffness, we wanted to make sure that so this is the target spectrum. This is a motion that we picked, so the red line is an actual ground motion. We modified it so that from this point to this point, your spectrum is within plus minus 30%. That guidance came from one of the old documents produced by Seismic, saying that if you do that, that gives you another idea in terms of how a structure should be tested. So we took 2 different ideas. In the old days, they would do spectrum compatible. This is another recommendation. We said, okay, we'll just run through both of them and see how well it performs. By doing that, we have tested the spectrum compatible and gives us a lot more information about if you design it for the design earthquakes, how well it performs. So we target, say, 2% drift, do we get 2% drift? Things like that we can learn. The other one gives you the unexpected motion that will have an unexpected peak or a cycle, how well the structure will perform. So if you're running analysis, you should kind of look at both sides of it rather than just using one set of analysis. So ideally, if you're doing a shake table test, all you have to do is, this is the shake table here, this is the foundation, here is the post, this pocket was put in so that we can access the post tensioning, so we can hold the anchorage and then actually apply the post tensioning. This is this effective seismic height calculator, so that's where your seismic inertia should be generated. You could leave a mass here, so that mass will be generating the seismic inertia. Alternatively, this is a setup that they use at the University of Nevada, Reno test facility. They actually put the mass outside, the required mass, because it's easier to support. Everything is pin-ended. So, and you have a rigid link to it. This is a rigid link. So as it moves back and forth, basically this mass is activating the inertia effects directly. The huge advantage of this concept, instead of putting a mass there, by doing that, obviously you don't have to have a lot of details in terms of how you're going to be supporting the mass. It's supported outside on a pin-based system, so it doesn't have any resistance, it just goes back and forth. The only thing holding is this rigid link. Because it's a rigid link, we put a load cell at one end, so we can actually know the inertia force coming into the system as well. So we can quantify the inertia. So that's the other advantage as well. So we know what inertia force is being generated because the seismic mass was sitting on the side.
Just to clarify, there is a shake table.
Correct.
And there is a base motion. And then at the top, why is that being required?
So the shake table, when it shakes,
Yes.
this mass technically should be that red dot. That's where the mass should be.
Yes.
So as I shake, this mass is going to go through acceleration and create the inertia force.
Yes.
But that inertia force that inertia force is what's going to create the movement that should be resisted by the system.
Yes.
The problem with this is that it is harder to put the mass at this location because you had to have an elaborate system, and basically these two blocks should be attached to it and they have to go for the ride. What this is we took the mass out and put it outside. This is supported on a frame. All of this is a pin-ended. So if I remove this this rigid link and push on it, it doesn't have anything to resist. It will just fall down. So you just go for the ride. But by isolating it as it goes, so it's almost, we put the mass on the side here, right? It doesn't matter if I put it right here. It's a seismic mass, a single rocking. But again, for the supporting system, this is much simpler to develop. So it's the same thing happening. So inertia is generated because this rigid link is transferring acceleration, creating the inertia. It comes back because it cannot resist the force, this system itself, and therefore, so if you're trying to do this with the platform, that platform also rotates, instability, you got a lot of headaches with it. Any other questions? Okay, I want to show you some video here so that you can see doing a quasi-static testing versus shake table test. So these walls actually run, go through motion faster because we are reducing the scale. That means you have to apply the motion faster as well to compensate for or maintain the scalability between the two. So the first one I want to look at is this particular test. So it's a shake table test of a rocking structure. So this is an unbonded rocking board. So let's take a look at this. Oops. Okay, I want you to pay attention to a couple of things here. So it's a single rocking wall. So the wall is being excited by the shaking at the base. Inertia effect is created. Look at the rock. After a few shaking, it just comes to stop on its own, right? So the only damping that comes in is the impact damping that we were expecting. And if any system, like obviously you have some inherent viscous damping in the system, so that's also play into it. But the point I want you to make is, if you shake like that, they will come to a rest. The question is, can they come to a rest in a reasonable time and not demanding too much displacement? I think that's a question that we are trying to answer, right? So they go through a fairly large movement, but post-tension is intact. We went through one motion, and the structure now recenter because the elastic force pulled it back. So after the earthquake, you won't even know the building has gone through any earthquake motion. This is, I'm just picking and choosing, and there are some videos online that you can see it as well. So this is, I want to look at response here, which is, so this is the base of the wall. I think some of you asked questions. So basically, these are all LED sensors. The problem with the shake table is that when you put these sensors, they need to be responding fast enough, and your data acquisition should be able to collect the data fast enough. The LED system, we believed, was able to collect the data faster. So each of the dot can give us displacement, velocity, relative displacement, and things like that. So when the wall come and hit, basically it goes into one angular velocity. So it basically tells you how much kinetic energy it's approaching the foundation. Then it reverses back, it loses some of the energy and reverses with a different velocity. So we were interested in capturing every time it hit and go back, how much are we losing it? So the reason I go through this is to say that I'm not just arm waving. These are based on actual evaluation. So I want you to look at and see.
The on-site work, off-site, and there's costs and construction time on-site. Critical aspects to the design of precast that you need to know when considering design. So if we're going through some of those best practices that have been developed over time from the temporary works.
I think some other video got started for some reason.
Arguably one of the most unique features of precast is the fact that it transport from site and bring it to the place that it needs to be installed. This leads to a couple of things that you need to consider early on in your design.
Okay, let me figure out. I think I got some other. I found a couple of videos that I thought I was going to share. I think one of them got started here. It's not this one. I don't even find that where it's causing. So basically, I want you to see actual rocking. So when you do a quasi-static versus actual rocking, so this is the few things I want you to observe in this particular video. They go back and forth in terms of rocking. It's actually the same wall as the previous one, except that we are focusing on what's happening at the toe of the wall. You see some concrete got spalled off, so those are cover concrete basically. Every time it hits, there's a spalled off the cover concrete. It's not compromise the actual core of the structure. So this is what people were trying to prevent by putting steel armor so that when it hit, it doesn't spoil off the concrete. What we figured out was that when you establish a contact with the grout pad, so if you look at the plan view, if this is the wall, and if this is your core, basically what you're seeing is these are the concrete coming off. So in the final test, what we did was we eliminated the steel channel, and we only put the grout just underneath this core region, so that they don't actually experience any impact, all of this cover region. And that actually solved the problem. So you don't need to put the steel channel and still prevent that spalling that you're seeing here so let me just play both of them, the one after the other. So the first one, this is the actual wall. Now the volume is completely gone. Okay. So you could see how it rocks back and forth, right? That motion is what you see in the second video here. So if you look at the amount of force that it comes down with and hit and bounce back, obviously you can appreciate there's energy being lost each time. So the plan was to try to capture what's the energy loss that we would go through. So this is one of the pre-vec, which has energy dissipation. So you can see how that performed. So these are side-by-side comparison. So these are side-by-side comparison. Both are subjected to the same earthquake. What you notice here is that the wall doesn't really rock as much as the previous wall because you have the hysteretic energy dissipation coming in. So they don't rock as much as the previous one, and they don't go through large number of free cycles as much as the previous one. So energy dissipation does provide benefit. When you look at it side by side, they clearly show. So again, take a look at it. They come to rest pretty quickly because you have energy dissipation in the system. Now, if you focus on the connector as to what the connector is doing, you could see in this video how the connector is being deforming. So the movement that you see basically goes through and dissipates the energy, right? So first one, unbounded post-tensioning, no damping. It is rocking quite a bit. Second one is a pre-vec system with the energy dissipation. The important thing to notice is that we said wall is not rocking as fast as before energy dissipation kicks in. So it has actually also altered the impact damping associated with that second system as well, because you put in energy dissipation here. So the energy dissipation is taking place through here. That's what you're seeing in this particular video. So if you look at the single rocking wall test observation, you could see they go through a motion. This is particularly the observation after the design level earthquake. We designed the wall to resist the design level earthquake, and you could see after the test, we did spoil off some concrete, but the wall is back to its original position, and that's how it looks. Now, you've seen enough of cast in place. By the time you go through design level, you would have caused cracking, you would have caused some spoiling. None of that comes in here. The bottom row is basically the equivalent pre-wreck now. They do the exact same thing, except that we deform and dissipated some energy through these systems. If you look at the amount of energy dissipation, this is the single rocking wall. You could see the energy dissipation is definitely small amount. But even though we subjected that wall to design earthquake and the corresponding energy dissipation appears small, that wall actually came to rest after some cycles. So then one questions, what I said at the beginning, okay, how much damping do we need it? And what was the disadvantage of reducing the damping pretty significantly with a single rocking? How much energy dissipation can you actually dissipate through the single rocking? So we also looked at some evaluation compared to the single rocking versus the pre-wreck system. You could say the pre-wreck system dissipated more energy. Single rocking wall dissipated less energy. We did say that if you reduce the amount of damping, maybe it's going to displace more. And you could say it displays somewhat more than the pre-wreck system, but it's not very excessive, right? So you can estimate and decide. So one is in the order of 18% damping. We eliminated that supplemental damping of 18%. So 15% we eliminated. The displacement went up by, 20%, pick a number. The key is to maintain the post-tensioning force. So if you look at the post-tensioning force, what you see here is you applied some initial post-tensioning, so that's why this number is not 0. So initially your post-tensioning was here. As the wall rocked, it increases the post-tensioning, and as the wall come back to 0 displacement, it's come back here, go back here, and come back here. You see the symmetry? So they're just doing the same thing because center of the post-tensioning steel is at the center. You see that this side, the displacement was higher than the displacement here because the earthquake happened to have a larger excursion in one direction than the other. So in essence, they behave in a symmetric fashion and perform fairly well, given, we were expecting when you cut down the damping by such a large amount, we would have significantly different results, but that was not what we found. If you cause, so this is something I want you to understand, if you cause inelasticity, we did experience in some cases, then your post-tensioning stress actually come down. So it went up here, yielded the steel, came down here. So we are now here, implying that we lost quite a bit of post-tensioning. So we were able to estimate how much post-tensioning. In this case, it looks like a significant amount because we did actually test this to much large number of earthquakes. But you should be able to estimate and say how far we can allow this to take place. We develop models and things like that, so I'm not going to go into the details here. Let me see what some of the other thing I wanted to cover. The two topics I wanted to cover is, one is the evaluation and just in terms of how it will perform. So let me just show you quickly. For these systems, these are much simpler system, and they respond more in an elastic manner, and getting good predictions are also fairly easy. You don't need to have complex models. So you could see some of the prediction the student did here, experimental versus the theoretical curve. So those four are for a single rocking wall, and these are for the Prevex system. So you can get fairly good accuracy with a very simple model. When they released this EQ1, EQ2, EQ3 level intensity motion, they also proposed some idea in terms of expectation if your structure to be functional. So that Seismic introduced this concept of earthquake performance level. So you could see these are the earthquake levels, and these are the seismic performance objectives, and then these are the different levels of what you're looking for. So the question is, after the earthquake, do you want the structure to be life safety alone, or you want the structure to be occupiable, or you want the structure to reach a near collapse? So cast in place is done pretty much in this fashion. So if you come to the EQ4, your structure is going to land somewhere here. What we felt was we could pick the EQ level. So if I take a design level earthquake, I could choose it to be occupiable, and basically that tells me this path would be a better option. So this means I need to be able to control the displacement so that maximum displacement is reaches this, not this path. So this is where going from life safety design to more functional building. So we felt like with the jointed system and unbounded post-tensioning, you can actually promote this idea of you can design these more resilient structures with the potential for being functional after the earthquakes. So we set some criteria as to, in order for this to be functional, what would be the structure should do. So, for example, we had for each of the earthquake level, we had residual drift, because you don't want to have the structure to lean after the earthquake. So the residual drift is a criteria. We had set acceleration on the floor. So single rocking wall is going faster and maybe accelerating more. That means your contents may be getting damaged more in a single rocking wall structure versus a Prevex system. So we put some limitations. So these limitations come in based on some recommendations that people have done for building safety, resilient design, or how to protect content in a structure. So those ones is what we pulled together. The other variable we used was the maximum lateral drift, right? So if the structure may perform well, but if it's displacing twice as much, maybe that's not a good thing. Things are going to be thrown around and people may not feel comfortable. It could cause displacement compatibility problem for the gravity systems. So all of that stuff. So for each case, we have a threshold value. So for each of the earthquakes, you could see we define the residual drift, so it should not reach targeted value. It should not exceed the targeted value. Same applies here. If it exceeds the targeted value, we will report what that number is. The top walls are, you can see it's all single rocking wall. The bottom ones are Prevex system. I just don't want you to go into the numbers, but if you look at the Prevex system, the number of times we exceeded, so this is after going through, anywhere from 12 to 15 earthquakes, and some of them are pretty heavy. It's not just one event. But after doing all of the tests, if you look at the Prevex system, there are 1, 2, just don't worry about the numbers, 1, 2, 3, 4, maybe 5, 6 times we exceeded it. One is it, so none of them failed, collapsed or anything like that. We exceeded our target number few times, which should be expected in any earthquakes, because you're bound to have energy, exercise the building further out. But for the majority, you could see it satisfied all of our performance objectives. Now, if you have exceeded, so these are 20%, 28%, this is pretty significant, it's 100%. Again, we were studying one specific thing, so we investigated what the issue is. So that's how you look at this one. Now you come to the single rocking wall, maybe you have more numbers exceeded, right? So there's all of them lateral drift exceeded, but the wall didn't fall down, but it did exceed. So that's 1, 2, 3, 4, 5. There is a lateral drift exceeded here. So typically they actually gone through a lot more displacement than we expected, or what the code would allow you to do, or code expect you to have. But the surprising thing was that structure survived and performed satisfactorily. So I've shown you the single rocking wall, the amount of steel we put in. I've shown you how this is connected. Just run a strand or two, that's your connection. And they're doing really well, because most of the energy dissipation is actually coming from the impact itself. And each time it's rocked back and forth, it's just take out, it's not a significant amount. You just take 3% energy out. Next impact, it takes another 3% out. So just eat away the energy, and that's what dissipating energy. So for the 18% damping we put in here, you can argue that it improved performance, but it's not day and night difference. It shows improvement. So my argument is that, okay, so this is maybe not enough, maybe this is better, but maybe we don't need an 18%, maybe we put a 12%, this should be good enough. You take a non-seismic case, if you say you want to put in a strand and no reinforcement in the panel, I don't think anybody will approve it. But this tells you, even for non-seismic, you can actually simplify a lot of the details in terms of the amount of reinforcement and in terms of how you establish a connection. If it happens to have an earthquake, it actually will survive. Like even go to low seismic, moderate seismic, you don't need anything. You just put in, this is for, look at that, this is exceeded at the maximum considered earthquake in a high seismic zone. If you're in a moderate seismic zone, I don't think you're going to go past, even this. Yeah. So, really reliable system for low, moderate seismicity, fairly easily you can deploy it. And Precaster would love it because a very simple detail, they can cast these panels and transfer to the site fairly easily. So, even though we shifted more towards seismic, I want you to think about non-seismic and how one can simplify these details and deploy it for a non-seismic application. It's a very attractive in terms of how you can establish connectivity. Even in the US, people are still reluctant to use because they always like to have when you cast the grout thing, they feel good that it's rigidly connected. Yeah. But I think this design guidance and things like that we can force, and when you do testing, you can bring some of this evaluation.
Actually, I know you told, I think even for on-seismic, it's a no-brainer.
Yeah.
Good. Now, corrosion, you said it could be an issue. But are there any efforts to, because the amount of strand what you're going to use is not going to be that significant.
Yeah.
Have they explored stainless steel?
The US, they have introduced it, but I don't think they're using extensively. So they do, for these systems, they do pump grease in it, in the duct.
Grease.
Yeah, they pump these things, and then for the in region, they do provide some partial bonding also, anchorage concern, for example. But in the same question, you go to the bridge world. I don't know about here. In the US, bridge and buildings are worked like this. They will have like 300-meter unbounded post tensioning going from one end to the other. Nobody questioned. You put it in like a 3-meter wall, they say, oh, why are we doing this? So,
But even if which is here, unbounded is not very common.
where?
Here.
Yeah, that's what I'm saying. Because of the concern. But what I'm saying is that, we had, so this is, I don't know, it's got 1, 2, 3, yeah, let's say this is a 10 volts or 8 volts. We did couple of other volts, 10 volts, going through like 10 times 12, 120 earthquakes. I never lost a strand, is what I'm saying, right? Whether we tested fast, slow, pre-wag, single rocking wall. So, but the question is, the long run, is a corrosion or something going to come in? So, we did study the strands separately. We did, if you have interest, I can go through that, some of it tomorrow. But we did find that if you keep stretching it, so I don't know if you guys do strand testing in the lab. Okay, when you do it, how do you hold it at the ends?
We put the regular
Anchorage, right? So if you put it, you never break the strand. You always break it at the end. So the same thing happens there, right? Because strand has a strain limit of 0.008 or whatever. You will never reach there because wedges cut into it faster. So there is a way to test this one. So the wedge has to be, I think the one wedge we use is about, I would say easily, I don't know, I would say 10 centimeter long. So those ones are specifically designed to fracture the strand itself. So that's not feasible. So we took that information and modified the tapering to show. I don't think we completely eliminated it, but we showed that you can actually increase the
anchorage, we made it longer.
It's not long in the sense, big. It's increased by a centimeter or a few millimeters, basically. The goal is to adjusting the tapering angle will change whether it's going to cut in or not. Yeah. So you can certainly improve it. And then these are remaining elastic. So typically they have fairly, they still have a fairly large travel. But yeah, I mean, this is something that people have to understand and appreciate the value of it. But anyway, I just wanted you to see the impact of it in terms of how many times we violated our condition. And acceleration was not an issue. So these are the different things. This is on the design side, so I wouldn't go into the details. So because they exceeded the value, we made some recommendation in terms of how you can modify this, fine-tune it so that you can avoid some of the instances where we exceeded the value using a displacement base. So what we found was that the damping based on the evaluation, this is what you see here on the y-axis is the base shear, and this is the damping ratio. So if the system has a certain amount of damping, your base shear is going to be this value. Don't worry about the unit, but let's say it's a 30 units. But if you're doing a single rocking wall, your base shear will go up. And so instead of 3 volts, maybe you put 4 volts. But again, wall panel doesn't have a lot of reinforcement. So 4 volt doesn't cost a significant amount. By doing this manipulation, you can actually control both walls without causing any, large drift, for example, what we've seen. So that's what this is all about. So you can actually figure out as the damping go down, maybe you increase the design force slightly, and you will improve the performance of the structure is what the idea was. Okay, so this slides now. Hopefully, you understand the two behavior one by one. So you could look at this particular slide and see how much damping that we estimated for these systems. It's hard for me to read. Okay, so let's see. The first two are single rocking wall. The hysteretic action brought 2.8, 3.65, so those are pretty small number. We assume a viscous damping, and then radiation damping we were trying to quantify. So those walls didn't have more than 5-6% of damping. The Prevex system, the hysteretic action, you can say it went all the way to 16.9%. So you put in an 18%, but doesn't mean the earthquake will maximize all 18%. The number 16.9 tells you that it's actually performing to the expectation that you are providing to the system. So if you provide more damping, obviously it's a displacement dependent. The more displacement, the more damping will be utilized. But I want you to realize, so this is what we proposed. We said if you decreasing the damping, maybe your base shear has to go up. And that's what we proposed, right? Now if you go back and look at some of the data we collected, these structures had this much damping in the system. So it's in the maximum is close to 20%. And then this is the lower end here, 7% damping. All of these points comes above it. None of these structures actually violated our performance objective. These data points fall below, they violated our objectives. So again, it implies that what we are proposing is maybe reasonable. There's only one data point, it's above, and then, but did violate some of our conditions. Again, you're going to get one or two anomaly because of the nature of the earthquake itself. So, you know, the damping is kind of, people think as something is inherent in the system. We hardly do evaluation unless you do a dynamic testing. So that's one advantage for us. We were going after it, so we did the shake table to get that information. Hysteretic damping was calculated based on the hysteretic loop that we obtained, so that was pretty reflective of how much damping is coming in from the system. So we were able to look at different damping in different form. So you could see some of them had 5-6% damping, especially the single rocking wall, whereas the Prevex had up to 20% damping. So, you know, 1/3 or less damping in the single rocking wall, but overall, we didn't completely lose a wall in any of those tests. So that's important piece to realize. Any questions here? I know there were some questions asked in the break. Go ahead.
Other walls from L18, other full length walls. I'm asking because if they are full length walls, full height walls, how are they rocking? Because the rocking will tend to move it up.
So these are rigid wall. Think of it as a rigid wall. They are full length. So precaster can choose to cut the wall in 2 panels, if you like, right? If a 6-story, they may bring the wall in 2 segment or 3 segment. Between the walls, so there's a concept people use in the precast world is when you establish a connection, is the connection is going to be stronger than the member or weaker than the member. So that's what the emulation concept kind of went after. So if you make the connection weaker, then connection will open up. If you make the connection stronger, then member will deform or go through inelastic action. So when you establish this connection at a higher level, then they establish the connection to be stronger. So there's no other places the wall will open up. There are 1 or 2 research actually looked at opening it up at a couple of different places rather than one location. I really don't see a benefit. Now your other question is, how would they rock? Well, if they're rigid walls, unless you restrain the rocking, they should rock because they're rigid and they're not held anywhere. So the only problem that interferes is that if you connect the floor to the wall, for example, I think that's what you are also asking, right? The wall comes in, the floor comes in, you run the rebar into the floor, into the wall, and then the wall has to now take the floor with it. So I think I showed a slide earlier, and I'll show it again. When that happens, then even the plastic action that takes place within the floor will restrain the wall from going. So it will not rock as much as you envision as an isolated wall.
But when you, I think when you have like say 6-story, a precast makes two story height, then obviously that interface can become potential locations of.
No, so that's what I'm saying. So what they do is they make sure, at least in our case, so that's what we did. So so let's say this is one panel, so make it simple. We have a second panel here. So the tendon will be run from top to bottom. Here they will use typically a sleeve connection. So that's very common. They will put a grout pad and they will establish connection. So these are all connected together. They're not prevented from opening. So it will be designed to be stronger. So if you say this is your, for simplicity, say this is your bending moment, they will make sure that your bending moment is, the capacity here is out here somewhere. It won't open up. Go ahead.
After an earthquake, there's a pre-stress loss. Do we replace tension in the tendons?
Yeah, so if you lose pre-stressing, you literally have to replace the tendon because you cannot stretch it more and try to get more out of it because you're already in the inelastic path. So typically, as I said last time, so if this is strain versus stress for the pre-stressing, let's say this is your curve. You design them to be here with the initial stress. During the earthquakes, they go up to somewhere here. And then they come back to this. That's the ideal situation. Occasionally, you may go somewhere here, and then you come down here. If you come down here, obviously you lost the post-tensioning, and you have a permanent strain. So if you stretch it again, it's going to go and stay here. So the question is, how big is it? Can you tolerate this value? So what we have done is we've done some studies to say if this goes into the plastic or if you lose, I can't remember the number, is it 10 or 15%, the structure will survive. So if you lose 10%, 15%, you're in the curved portion of it, maybe it's acceptable. But if it's significant, then you have to replace the tendon.
So then how do we do it? Is there some place anchoring?
If it's unbonded, basically you remove the anchorages, then you can run the cable again.
Dismantle the whole wall and everything.
What's that?
Dismantle the wall and
No. So these are unbonded. So if you remove the anchorage here, you can pull the strand out, right?
but then my question is where does it from, because it's all the way to the sea.
Yeah, you will have provisions for that, typically anchorages. In bridges also, in post-tension girders, if it is unbonded, I can
Remove it.
twist it, I can remove, right? So the same way, when you design it, you have access regions for.
Yeah. So at that time, that was the industry plan. Like, yeah, we'll have access holes, access point where they can cut the tendon, pull pieces out. They had a vision, but practically we haven't really gone all the way, right? We haven't built hundreds of them and then some damage and we replace. There's a vision as to how we would do it. The industry does some great innovation when it comes to replacing. So they thought through what the steps are. It's not, so in some of these tests, actually, we try to remove, like, can we remove the wedges easily? So they can be done fairly easily. So they don't get jammed and things like that. They just pull back and then the wedges comes out. They cannot use any of the wedges or the anchor head. They go through some localized damage, but you have to put a new, you're not replacing the entire building, right? So the cost is nothing. Go ahead.
In New Zealand, I think your colleague
Yeah.
was pushing it in a big way.
They did use some of the structures. They actually pushed more so towards the timber. There's a timber industry got all excited. So the prefab is actually installed in New Zealand on a timber structure.
So even the hospital building we kept telling,
Yeah.
after an earthquake.
So that was basically a prefab system. As we tested it, they installed it. That survived the earthquake pretty good without any damage. There was some deformation to the connectors they seen. Is that mine or? So, but I think I just want you to get a feel for how these systems, how people have kind of overestimated or overthought some of these systems, and some of the simple system was eliminated. And then the other, my main message has been that, don't force any of these new structures, new elements, or new material to behave like, older, some other material. They're not, I think I see a lot in UHPC world. They try to do, hey, I need to do this. Like if you try to use UHPC in Seismic, they perform very differently. So the question is, can I rely on this behavior, and can it survive an earthquake? So if I don't think about cast in place or steel, then I should be able to come up with a plan for UHPC and then push that to go in that direction. Question, any other questions, comments? So briefly, in these tests, what we found was when the design level earthquake comes, so when I say design level earthquake, it doesn't matter whether spectrum compatible you pick, the damage of the system was almost negligible. In cast in place, you've seen enough pictures to think that what the plastic action means. Typically, the self-centering nature, so when it goes back and forth after the earthquake, they come back to its original position. That's a huge benefit of the system compared to cast in place. The elastic force in the pre-stressing system basically bring the structure back. So you don't have to come back to the original position after the peak displacement. The shaking that goes through back and forth eventually bring the structure down. We made some recommendation as to, some guidance as to you don't put too much damping, then obviously it will not recenter. So we can tackle that fairly adequately. In terms of meeting the performance criteria, for the most part, the structures met their expectations. There's some anomalies that you've seen, more so with the single rocking than, and then we made some recommendation as to how that should be tackled. Let's see, I don't want to go into the design. I'll just show you a couple of these images. So when you rock these walls like as a single rocking wall, we were able to, based on the velocity in the system, we were able to capture the amount of energy dissipation takes place. So you could see as the time went by, so you see kind of a step function. The step function basically tells you every impact that you have. So every time you impact, you lose some energy. At next impact, you lose some energy. You go to the next impact. So whatever the energy put in, by the time it comes here, so you see that wall is slowing down, that's what the energy dissipation, so it's kind of rocking back and forth. But by the time you hit this point, all input energy has been dissipated by the impact that has gone through. So we were able to quantify that wasn't quantified before in terms of how much loss that you could expect for these walls. So that gives you your equal and viscous damping value that you want to use for design. We made some other design recommendation as well as to how it should be done. And then, okay, this is the other point I wanted to emphasize here. When you do a pre-vex system or when you combine like two systems, one is helping with the recentering, the other is dissipating energy. This, you see that this peak goes here, unload, it comes here. So if I look at that peak, it doesn't recenter. These one has some permanent displacement. If it's a cast in place, you'll be right here. So obviously you got rid of a lot of these values. What we found was that this curve comes within 30% or 25% of the peak displacement. The shakedown that takes place after the earthquake actually brings the structure back. So that is a guidance in terms of how much energy dissipation you want to put in. Some people think that more energy dissipation is good, and they put like 35% because connectors are cheap, I'll put more energy dissipation. But if you do that, you won't get the recentering. And you don't shake too much, but 1 or 2 peak cycles will go through, but then structure will have a permanent displacement. So we recommended what would be the ideal position so that you can rely on what they call a shakedown. So after the peak excursion that took place, structure goes back and forth because you still have the energy coming in. You have the energy in the system. So they don't, they have to go through some free vibration back and forth. So we're saying that if this value is 25%, maybe it's 30% of this peak value. So if you come straight down, basically you're retaining a permanent displacement will be almost 100%. So if this value is reduced within some numbers, then we believe that recentering will be achieved. So we introduced a jointed system, we promoted the idea, no damage, recentering, minimize damping. Then you have to make sure that every element is put in the place so the structure can do what you're expecting it to do. All right, how are we doing with time? Where is Rendra? Two other topics that I wanted to address. One is a little more into the energy dissipation, so maybe I'll talk about that. And the second topic is the floor interaction that we talked about, right? So we'll cover that maybe a little bit tomorrow. I think I have some time in the morning.
Afternoon, it's another 2 speakers are going to talk.
Afternoon tomorrow. Yeah, I just need the morning, and then we will do some. Do you tell them that you're going to do some quiz or evaluation tomorrow? You guys know that? You're studying?
Yeah, I think we have posted it. It's just a conceptual. We'll have a short, objective type exam to satisfy the requirements for the certification.
And plus, figure out what you learned.
Yeah. That's more important.
I think Professor Amalan will come up with a good question based on the pre-stressing he offered. Yeah, so conceptually, so don't panic, students don't sleep tonight and study and all that stuff. But think of simple things that you can come up with based on what you learn. Can you differentiate the different system? Can you sketch out crack patterns? Can you, things like that, right? It will be helpful in terms of, so we'll come up with a plan for that. I will briefly talk about this. I don't know if you're sightseeing, you can start thinking about rocking now in the. So the rocking concept was people have looked at it in the 60s. What surprised people was you go to these structures, they go through earthquakes and they don't fall down. So Professor Hausner was intrigued by this, and he did the very first paper actually on rocking of structures was published by him.
These look like Greek and Roman structures.
But yeah, this was a Greek in Greece. But the question was, these are standing there for thousands of years, and that region has gone through earthquakes. Why haven't they fall down? So it turned out that, I think the other thing I mentioned to you was that, in cemeteries, they have these monuments. In the old days, they built the tall monuments. And they don't establish any connection. They actually, put on large support, something they built, and I don't know, they put some kind of a pad and put it in place. And they found that in the earthquake region, not all of them actually fall down. Some of them survive, some of them don't. So that's when the Hausner looked at what's the aspect ratio issue that influences a free rocking response. That's how the whole thing was. So if you are interested, there's a famous paper that Hausner did back in the 60s, I believe. We did find one mistake in that assumption he made when he applied to this. So we did modify, it actually does a pretty good job. So it's all about calculating, I think what he was calculating is a coefficient of restitution. So it's a good example is to, if you think of a ball, like take a tennis ball and bounce it on the floor, each bounce, it goes down, right? So the velocity that goes towards and then bounce back, there's a ratio between the two. That ratio remained constant, roughly constant. And that is what defined the coefficient of restitution. So he was trying to figure out what is the coefficient of restitution if a concrete rock on a concrete versus concrete rock on something. We did take it to the next level in the single rocking wall. So remember we said single rocking wall, you can if the damping is less, you can increase the design force. The design force, if it's a small increase is one thing, but if it's increased by 50%, people then say it's going to add cost to it. So one of the things we investigated for single rocking wall was to put a rubber interface between the foundation and the wall panel. So if you do that, you can add another 3%, 4% damping depending on the type of rubber. I think there are some rubber are can dissipate more energy than some of the other quality. We're looking at like 25 millimeter, 30 millimeter thick rubber. The only challenge is replacing those rubbers after an event if it get bad. So we would put the rubber only at the end regions where we can hopefully remove and replace it. So for single rocking wall, that's another thing that we looked at it. And we looked at that based on basically how much more damping you need to put in. So the energy dissipation, the coefficient of restitution, the concept was established by Hausner initially. And so you could see, so if the coefficient of restitution is 1, means it actually bounces back 100%. So goes with the same velocity, bounces back with 100%. There's no such thing in the world that can do that. So if you bounce something, it will eventually come to rest, because each time it impacts, it loses some energy. So the different points that you see here is the different structures, different systems that people have established, and then whatever they reported as a coefficient of restitution. This theoretical curve tells you how they follow a trend here as well. The point that I wanted to emphasize here is briefly, let me see what slide I want to go to. So we wanted to quantify, because when you do a finite element or some kind of analytical model, you are not able to incorporate this damping, because if you don't incorporate, you're not getting the results accurately. What we did was, we did come up with a scope of research where we wanted to quantify the energy dissipation in a free and controlled rocking. So if it rocked freely versus if it rocked, so the controlled rocking, the moment you introduce control, it alters the response itself. So the amount of energy dissipation associated with that will be different. And then, yeah, we create some models and integrate it into the analysis tools. So the student who works on it is actually Dimitrios. Dimitrios took a class with Professor Amaran when he was at Iowa State University. So you can see these are the systems that we use to quantify the free rocking motion and figure out some of the variable as to, is that for concrete structures specifically, is that drift dependent? 1% drift, does it cause the same coefficient of restitution as 3%? How much energy dissipation can you expect? If you put a rubber interface, will the damping goes up? So again, these are all available in literature. So in the control rocking, in each case, we will pull it and let it rock. In control rocking, we put a post-tensioning in the middle. In the free rocking, we don't do anything. We just pull and let it go. And so these are all same topics that we discuss in terms of systems. And then you could see where the mass is put in place as an equivalent mass. And you can see the mass is positioned here. We also relocated the mass in some cases to create different period for the structure, so we can study the period influence as well. So you can see what the systems looks like. And then we were able to focus and capture data right here in terms of the angular velocity at which point where it goes. So if you look at the system, there's a cable system here. So basically we pull on it and then release the cable and it just freely rocks. So let me just show you how this system behave. I'm afraid the guy is still talking. I don't know how he's still there. Yeah, there's no video, so I'll just cut down the video. Okay, again, I want you to see when they rock. So it's released. So these are pretty large drift that you put in. It goes back and forth as you would expect, but eventually it's just come back to zero displacement. So we know that there's energy dissipation taking place. It does dissipate the energy that you put in, and so the first one is a free rocking. Second is a control rocking. This control rocking, basically, as soon as you engage the post-tensioning steel, it's going to apply the opposite direction motion. So it can't go more. So take a look one more time. So that's a control rocking. So it comes to the smaller displacement pretty quickly, as opposed to this is free rocking, where you let it go, it keeps going back and forth quite a bit, and it's a slower period as well, or lower period as well, because you don't have any restraining force pulling it back. So that's the typical response. You can see pretty uniform. So mention that coefficient restitution, that dictates what the peak here is going to be with respect to the previous peak and vice versa. So there are two responses here. One is a free rocking, the red is a controlled rocking. And if you look at the accumulated energy dissipation, the red curve, which is the controlled rocking, dissipate more energy than the free rocking body. That's why the free rocking is slower and goes for longer duration shaking as opposed to the other one. Now, if you know what the angular velocity, how it approaches, you quantify the amount of energy that was in the system, what is the energy dissipation after the system, then you can figure out percentage of. So there's a small energy dissipation loss, but it takes place in each direction. So it eats away energy. So as you can see here on the left, it's slow but steady in terms of how the energy dissipation takes place. Now, if you throw in a hysteretic damping, this behavior will be altered. So that's why I said you cannot take that as a summation of all of them. The student did make some modification and to the models and able to capture. So obviously the pre-stressing force, so the change in pre-stressing force, that's an easier thing to capture. So you can see how well they match in terms of, so this is not very easy because impact loading, you had to add contact elements, you had to characterize how much, but you can manipulate, you can fine tune and reduce, but the advantage is that if you capture that accurately, then you can model it, run a dynamic analysis so that that will get activated automatically. So that's what we were trying to do. The free rocking, controlled rocking itself has a lot more stuff to learn from if anybody is interested. There's a lot of people, I think, after these rocking structures came to service, there's a lot of people around the world studied rocking of structures quite a bit, theoretically also.
Even for like large liquid storage tanks supported on ground. I know Professor Velasco.
Okay, he did back then.
About this rocking motion.
Yeah. Yeah, so those special cases people definitely studied, but I'm saying in the last 10 years, there's a lot of studies done because there's a lot of interest came about in terms of utilizing this rocking knowledge. But I think it's calmed down now, so people just go in a different direction. But it's a very complex topic. So in this particular case, we were trying to quantify the impact energy dissipation versus the viscous energy dissipation. So the viscous energy dissipation is typically roughly a constant value. So in these figures, you can say the purple ones are the impact energy dissipation. So you can quantify and you can characterize and figure out how much energy to be calculated. I don't want to just go into a lot more detail here. Let me see if there's anything else that. Yeah, I think what are we doing? Are we close to the time limit or what?
What's it?
What's the lunch time or what is it?
It's almost
12:41. Yeah, so the one thing I want to touch is the floor interaction. So I'll cover that tomorrow morning. I'll cover the floor interaction and then do a quiz, so the morning.
Couple of, industry folks,
But in the afternoon though, right?
today,
Yeah, but tomorrow afternoon? Oh, they have a lab tour or something.
yeah, today have the lab tour.
Yeah.
Electric gentleman is coming also. Mr. Anjane Prasad, is also very seasoned in Precast. With a lot of projects, so easier.
Local in Hyderabad? Okay.
Does he come? Prasad, Anjane Prasad? He's on the list.
Yeah, I think Professor Amaran said the first speaker is from his student, former student.
Yeah, he's doing a lot of interesting projects. That's why I wrote him in.